Now we are done with coordinate descent. What's next? As I was talking through, you realized, when I lose differentiability, a lot of my techniques stop working. So now we need to address that limitation. What if you have a convex function, but it is not smooth, like the L1 norm, or some other empirical risk minimization situation you're in, where you have something convex? Loss functions, since we designed them, they're usually not so crazy. You get cross entropy, some norm, but they are not necessarily always differentiable. So if I can do convex but not differentiable, maybe I get something for a general family of empirical risk minimization problems. So if I have differentiability, this was the definition of convexity: fy minus fx, gradient of fx times my y minus x. This was how it looked, right? So now I don't have this. If I don't have differentiability, what do? I need to find a proxy for the gradient vector, since I don't have gradient anymore. Okay? So that's the thing we will be addressing today, and probably also in the next lecture. So the definition for that is called subgradient. Let me walk you through this slowly, then I'll also show you pictures. So what's a subgradient? This is the vector v, and it is attached to a point x. It's subgradient at x, and it's a vector that satisfies this inequality for every dot y you could pick in your domain. So this is your x. This is any other y in your domain. Suppose domain is also convex, like your function, for simplicity. Then you would like this to be satisfied with this times the gradient. It's just really replacing that gradient in that inequality. Okay. But the point is, now that I lost differentiability, there might be more than one vectors that satisfies this inequality. When I have the gradient and differentiability, I knew that v is going to be that gradient. Now, potentially, I have many choices. And I need to try to pick, somehow the best one among them. So the situation gets a little more complicated, but we'll manage. Okay. And how does the story look if you look at it from a geometric perspective? So this is my point x, and this is fx, right? So let me try to write down that inequality and try to see it geometrically. So this is x fx. And suppose I got here y fy, right? Now look at that line segment. Since I have a convex function, that line segment is going to stay above the graph. Okay. Now let's look at the inequality. I need to get fy minus fx greater than or equal to my subgradient times y minus x. That's what I need. Very good. So it looks like y minus x is the most of the coordinates. Only the last one is the number fy fx. So my v cares about this y minus x, the subgradient vector. And for the last coordinate, we don't really do much. We just take fy minus fx, right? So the inequality goes like this, as you see it above. V will be dot product with y minus x. And this has got to be less than fy minus fx. So how does it look like? Think about like v minus x dot product should be less than this. How do I think about this? Well, maybe this. So let's put a -1 next to my v. Basically, this still did not fit with my geometric picture yet. I'm just trying to see things geometrically. Okay. So let's put a -1 next to my v. And by that, I think I'm going to be able to fit. So let's say I'm doing this. V -1, y minus x, fy minus fx. So this vector y minus x, fy minus fx, is literally the difference vector. So it's like this guy now. If I take this dot minus this dot, I got this vector. And that's literally this vector I'm writing here. And I'm going to go multiply it, dot product it with v, the subgradient candidate, and the minus 1, turns out. And then what do I get if I do that? Let's follow through. This will give you v minus x plus fx minus fy, right? And what do I want from this number? I want it to be negative. This is v, put fx there, fy there, you will get it to be less than 0. So that means basically, I want this dot product to be a negative number. So now it's more geometry. If I think about v and minus 1 vector together, when I take the dot product with this guy, it's got to be a negative thing, okay? So, okay, now I can kind of see. So this is my vector. What kind of vectors will give me a dot product negative? You know, half will be positive, half will be negative. And you have to have that negativity for any such vector I could draw. And this gives you the descent cone we talked about, basically. Okay, so this is how it goes. To be a subgradient vector, I should satisfy this inequality for any y you could pick from the domain. For every y, that v should behave like the gradient when I got the gradient. This is the same thing as we wrote this y minus x, fy minus fx, this vector basically, this guy is that vector right there, times v minus 1 being a negative number. That is the same thing as this v minus 1 being in that descent cone. Okay. And that's all your subgradient vectors. Now, I have like a whole bunch of choices of subgradient vectors now. You have all that cone, pick any vector there, you got your subgradient vector. So which one would be the best? Okay, that's like the next thing you need to address. Because when you're going to run an algorithm, let's say I'm going to do something like gradient descent, when I don't have the gradient, I will try to replace that gradient with this v, obviously, and I'm going to pick a step size per term. But what's the best v among all my options? Okay. Any questions so far? Hopefully things are making sense. I lost the gradient vector. I'm trying to replace it with it's like a proxy for that. But I apparently have a lot of choices. Now I need to pick the best among my choices to replace the gradient. And in the end, my goal is to still have a gradient descent or stochastic gradient descent like algorithm, where the gradient vector is replaced with the subgradient vector. And still try to prove guarantees. Okay, very good. And now some basic stuff about this kind of things that people realized. First question is like, do I always have a subgradient? Well, as soon as you got a cone like this, you got a subgradient for yourself. So what does that mean? That means okay, let me just walk you through the facts. I'm not going to do the proofs. So first of all, if your stuff is differentiable, you recover back your good old gradient. So the definition makes sense. This is a sanity check. If I define something, and if I push it to the differentiable case, and if I don't recover what I already knew, that's a bad definition. So it makes sense. If it is differentiable, you only have one subgradient, and that's the gradient vector. That's it. And if you pick a point on the boundary, not on the boundary, I say here, I have to double check. You get a compact non-empty set. Okay. Now, what am I going to do with this? Let me give you the thing I wanted to do with this. Yeah, okay. Very good. Okay, suppose the subgradient vectors exist. What do I do with them? First thing that comes to my mind is, even if my function is not differentiable, I can try to look at that limit from one angle. What's differentiability? You take this limit from any t, you get some number, then we would call it differentiable, and then we would have our directional derivative, okay? So let's not allow t to be negative or positive. Let's pick a direction v and check how much change is happening in that direction. That will be my directional derivative now. And I would like to find a negative directional derivative and go perturb in that direction v with my gradient descent type idea. That's what I would like to do. Now, what is that directional derivative now that I lost differentiability? So it comes out as, let me show you what it is later. There is a lot of math to establish these things. It comes out as follows. Turns out what that directional derivative gives you is you look at all your options for subgradients. Okay. And then you multiply them with the direction v you picked. They will all give you a number. And you look at the biggest number. That gives you the directional derivative. Turns out. Okay. It takes time to prove this stuff. But at the end of the day, there seems to be like an optimal subgradient. You realize that's suprema. And for that particular u, it behaves like the differentiable intuition you got in mind. That's the main thing. Now, of course, the question becomes, how do I go find that optimal u? Because I'm going to run an algorithm with this. Okay? But at least, you know, to get here, I'll need to tell you a whole bunch of stuff. I'll skip over a lot of proofs. But that's going to be at least one, like, how can I say, milestone that allows you to establish things. Now, you know, if you pick that u nice, even if you did not pick the best one, suppose you did not achieve the suprema, fine. If you got suprema divided by 10, you at least got the thing you wanted divided by 10, okay? So you're gonna go try to create ways to find a decent subgradient vector. Okay, now before getting there, I need to tell you basic facts people established about this. I understand this stuff might be looking too methy and abstract, but it's a necessary development to be able to run algorithms without differentiability, basically. Okay, let me go through basic facts one by one now. First thing is I defined the directional derivative with only one side. Two-sided, I don't have that definition working. Do I have that critical point idea still? How did we do optimization before? If it is convex, gradient is 0, done. I don't have gradient anymore, what do I do? Okay. Intuitively, you expect gradient. What does gradient mean? At every coordinate, I have nothing to change. That's what gradient means. Gradient 0 means, I'm sorry. How did we know coordinate descent is working out for convex and differentiable? That was the first picture I showed you, like this ball. Gradient vector being 0 means every single coordinate, you're done, you're optimized, okay? Now replace that coordinate with any direction v you pick. Adam, you know, very nicely observed that, you know, if I would be able to not only do a coordinate, but any good direction, then I could do better. Now replace it with all the directions you could imagine. If in all of them, the directional derivative is 0 or bigger, then it's hard to find the direction to minimize. Because wherever you go, it's increasing. So that is like, this guy is probably a local minima, okay? And that's how it comes about. So if your directional derivatives defined only one-sided are behaving like you expect them to behave, then you know you're actually at a local minima, okay? That's the first thing. Very good. Let me skip over the proof. I'll give you a little exercise. I'll write it on canvas. It's very nice and regular. It's fun. It's good to play with this to get a sense. Basically, we keep using the definition of a convex function all over this place. And turns out, if you pick a direction, v, and if you're going in that direction, say a little bit, and here more, this ratio keeps increasing, turns out. It's very regular. So to get the minimum is literally going down the limit and making that 0. All right, this will be an exercise. It's working out super nice, basically. Now, basic facts you establish about this. Since there is that regularity, you can replace that complicated limit by an infimum. Go in your v direction a little bit, see how much you changed, divide it by how much you went, and try to pick the best such t. Okay. That'll give you this directional derivative, turns out. And then what else? It behaves super nice. If I'm taking directional derivative of a summation of functions, we can split it up. And then if you're multiplying with a number, taking directional derivative in that direction multiplied with a number, that comes out, you just put the number out to your usual directional derivative. And you could also even prove this directional derivative thing itself is like a convex function. Okay. So if you take like two directions, take a convex hull of the vectors, like I got two coordinates, I'm taking like half. Let's think about it this way. Okay. And what do I know about how big is that directional derivative? If I'm combining two vectors, turns out you take one by one and you put out that mixture you gave in. And this is, if you look at it, you take this as a function, right? This is definition of a convex function, basically. You evaluate it here at alpha v1 versus, I think you're able to see. So at the end, even this directional derivative comes out as a convex function. So everything is like convex and convex all over the place. That's why you can make this work. Okay. All right. Very good. Next, another characterization of a subgradient. I showed you the next theorem already, so you know this. The next theorem will say this guy, directional derivative, is actually the suprema. Take your direction v multiplied with all the subgradient vectors. Take the suprema, you will achieve this one. That's the next theorem. For now, the first theorem is to be a subgradient turns out to be equivalent, if and only if, that the directional derivative is going to be bigger than v times u. So if you found any u, when you do the dot with your v, if that number is less than the directional derivative, you found a decent u. It's a subgradient vector. Okay, that's it. And the best one would be the one that maximizes that number. That gives your best bang for your buck. Okay. So best subgradient vector would be the u that is equal to this one. But anybody that is smaller is a correct direction to go. Yeah. Okay. So very good. And as I said, the next theorem here is establishing that it is supremum. I was thinking when I was writing the notes, maybe this one is good to go through. Give me a sec to decide in terms of timing. Okay. Let me not go through the proof, but it's written in the lecture notes, and it's again very nice proof using a whole bunch of convexity properties. But the punchline is I showed you the first. Turns out the directional derivative comes out as literally the supremum number you get out of all that subgradient vectors. Okay, let me skip over the proof. But there is something weird that comes out of it. Suppose I'm looking at my directional derivative and I go pick the negative of the direction I was looking at. Then you multiply it with the negative, you would expect an equality here, but you don't have it. Turns out you have an inequality. Okay, but it follows immediately by the previous thing I just showed you. Let's go through it. So this guy is minus supremum minus v vector times all the subgradients. I'm just applying the theorem we just showed. And then this is the same thing as what? I'm claiming it's infimum uv. Is this right? Let me see. This looks a bit shaky to me because minus will come out. There's also another minus. So maybe this, I'm not sure about my proof idea here. Okay, we'll have to check this. This was looking right when I was writing, but now it doesn't look right. Okay, so I'll check on this. All right, the fact is true. It's established by many ways. Okay, so this should be true. Don't worry about that one. But the way I was proving it may be wrong. Let's see. Okay. So usually I look at once, then it comes out correct. But let's see. Okay. And then so if this was correct, then this guy should be less than this for any u since it's the infima. But we know the other guy is the suprema, so it's got to be bigger. That's apparently what I was thinking. But now I'm confused with this one. So let me not try to fix this proof right now. But at the end, forget about what I did. Check if this is true or not yourself. And the only thing you need to use is the theorem you have seen before. Okay, this one right here. Okay. But at the end, it's, even though everything is nice and working out, there is also still some weirdness because you lost differentiability. That's my main point. Okay. Let's keep going. Now, when you have a function f and a point x, this means the set of all subgradients. And that set also behaves super nice as the best you could imagine. You take a set, you multiply it by 2, by means you're enlarging it by 2. Turns out that comes out as the same as you have enlarged the function first and take the subgradients. Okay. Or you take two functions at a point x, sum up their subgradient sets. Turns out it's included. If you would have sum up the functions first, then take the subgradient set. So, one side I'm summing up functions, the other side I'm summing up sets. The fact that this works out at all is surprising, okay? So, one of them, do you remember we summed up sets once for fun? Maybe you forgot. Let me show you how that goes. Suppose I'm summing up a square plus a circle. So you put that circle across the square, you put it, and you're moving through and trying to see what you can get out of it. Take any point here and a point here, sum them up, okay? And it comes out like this. Take this guy on the corner, it's gonna be like that and going through. So the set summation gives you something like this. This would be the square, and this would be the circle being added up, basically. And what I'm saying here is, take these two sets, add them up this way. It comes out like if I would have add the functions first and do the set operation. At least it's included in that set, like that, okay? So this part still is working out much better than you could expect. And then if you have a linear change of variables, you're doing a function f after some matrix acted on your variables, again, it just comes out as what? You take the subgradient and then you multiply with that matrix. It almost looks like chain rule, okay? So all subgradient set only gets multiplied by the transpose of that matrix. All right, very good. Let me see if you need to see this part or not. Okay, now, very good. I have about 5 minutes. So now this is the reason we started this business. You get something differentiable. You add to it something convex, but not necessarily differentiable. We would like to optimize over, and I don't have a gradient vector. So we have seen in coordinate descent the very special case where this convex guy comes in coordinate by coordinate, like this graph examples or other examples, L1 norm, that we are able to handle just by coordinate descent. But that's not always the case. You get convex functions that can use a couple of variables, not only just one. Okay? And the entire reason for trying to do all the stuff we are trying to do, or people tried it, It's like trying to optimize with that kind of functions. Okay. So let me see what this machinery gives you. So let's not forget, this is our differentiable guy. There is a gradient here. This guy is not differentiable, just convex. Okay. So first of all, you got a necessary condition for optimality. For an x star to be the minima for such a function, turns out it is if and only if you take literally the zero vector and you check if you could take the gradient of the differentiable part and add to it a subgradient and achieve to zero. This is akin to the whole gradient being zero, so you're like at a critical point. I don't have gradient anymore for the non-differentiable part, so replacing it with a subgradient. And if you can find a subgradient satisfying this, you're done. Okay. And if you're in a very lucky case where your differentiable part is not only convex, but also like strongly convex, like an L2 norm, then the minima is also unique. Okay. Even though the other function was not differentiable. All right. And that's the guarantees we got for this kind of stuff. And now the only question remaining after you get all these guarantees is like ways to compute a subgradient vector quickly. Then after that, we'll play our usual tricks. Gradient descent, stochastic gradient descent, whatever. That's the only thing remaining that we did not do so far. Okay, let me see. I have like 2 minutes left. Probably that stuff is better addressed next time. I don't want to start something new. But if you want to Google a concrete algorithm after the stuff you have seen today, so I don't feel great that I did not show you an algorithm yet in this part. I showed you coordinate descent today. That was an algorithm. Okay. So if you want to Google something, Google proximal point method. That's the algorithm that's going to come out of this discussion for this type of general family of functions. And I think it's okay to finish it, not entering a new thing in the last 2 minutes.